homogeneous material. A beam element has the name material composition throughout, and therefore the mechanical properties at every position in the material. Therefore, the modulus of elasticity is constant throughout the beam element. A member in which material properties varies from one point to next in the member is called inhomogeneous or non-homogeneous. If a beam is composed of different types of material, then it must be divided up into elements that are each single homogeneous material. Otherwise, the solution will not be exact. Isotropic material. A beam element has the same mechanical and physical properties in all directions. That is, they are independent of directions. For instance, cutting out the tensile specimens, one in the x direction, one in the y direction, the other 45 degrees in the xy direction, other plane. A tension test on specimen will result in the same value for modulus of elasticity, yield strength, and ultimate strength. Most metals are considered isotropic. In contrast, fibrous materials such as wood typically have properties that are directionally dependent on, generally considered anisotropic, not isotropic. The proportional limit is not exceeded. It is assumed that the beam element is initially straight and unstressed. It is also assumed that the material does not yield, therefore the beam will be straight after the load is released. These assumptions mean that the beam must be made of an elastic material, one which will return to its original size and shape when all the loads are removed. If not stressed, pause the material elastic or proportional limit. It is also assumed that the beam is not stressed past the proportional limit, at which point the beam will take a permanent set and will not fully return to its original size and shape when all loads are removed below the proportional limit. An elastic material is in the linear elastic range where strain varies linearly with applied load and the stress varies linearly according to sigma is equal to E into strain, where E is the modulus of elasticity. Here, rigid body modes for one-dimensional beam elements. Rigid body motion occurs where forces or moment are applied to the unstrained mesh, that is body. The resulting in motion that occurs without any deformation in the entire mesh, that is body, since no strains occur during the rigid body motion. There can be no stresses developed in the mesh. In order to obtain unique firm solutions, rigid body motion must be constrained. If rigid body motion is not constrained, then a singular system of equations will result, since the determinant of the stiffness matrix is required to 0. There are two body modes for one-dimensional beam elements, a translation displacement bundle and the rotation bundle. The two rigid body modes can occur at the same time, resulting in a displacement and a rotation simultaneously. In order to eliminate rigid body motion in one-dimensional beam element, that is body, one must describe at least two nodal degrees of freedom, either true displacement or displacement under rotation. Degrees of freedom can be equal to 0 or non-zero known value as long as the element is restrained from rigid body motion. Deformation can take place when forces and moments are applied. For simplicity, we introduce the rigid body modes using a mesh composed of single element. When translational rigid body motion occurs, then there is a displacement at a local node 1 will be equal to the displacement at local nodes j. Since the displacement are equal, there is no strain developed in the element, and applied nodal forces can be element to move in rigid, that is non-deflected vertical motion, which can be either as shown below, or it can be downward direction depending on the direction of the applied force. A rigid body mode can be suppressed by prescribing a vertical nodal displacement. If rotational rigid body motion occurs, then the rotation is local node 1 will be equal to rotation at local nodes j, that is magnitude and direction. In this situation, the total nodal forces and or momentum applied to the element causes the element to rotate a rigid body either clockwise as shown below or counterclockwise depending on the direction of the applied forces and or momentum. The rigid body mode can be suppressed by prescribing a nodal translation or rotation. If translation and rotational rigid body motion occurs simultaneously, then a simple example of beam problem with or without rigid body motions. So the diagram 1 which specifies unstable rigid body mode condition present and determinant of mesh stiffness matrix that is equal to 0. Then equations dependent equations.